Okay, so something that actually properly belongs as part of linear algebra is this idea of solving linear programming problems. And these are part of a larger group of problems which are called optimization problems. Optimization, there we go. Optimization problems. So the big heading is optimization problems. The little heading are linear programming problems. All right. So in an optimization problem, the standard form is we're going to max or min some objective function subject to some set of constraints. Okay, so these are the things that we cannot change. This is the thing that we're trying to find either the maximum min or minimum value of. So let's just take a simple example from calculus of an optimization problem. This is not a linear programming problem, but an optimization problem. Okay, so let's take an example where we're going to maximize h of t when we have negative q over 2 times t squared plus v null of t at t plus h null. Okay, so from physics, this is basically the constant of gravity for wherever we are. We're going to probably put us on Earth here, but this is the constant of gravity. This is our initial velocity in meters per second, and this is going to be our initial height in meters. All right, so we're going to subject this to a series of constraints, okay? So the first one is that gravity is going to be 9.8, which is the constant of gravity here on Earth. The initial velocity is going to be 100 meters per second, and we're going to shoot from ground level. All right, so my h of t then becomes, well, let's see, this is negative 9.8 over 2 times t squared plus 100t. That's negative 4. So this should be 9.8, right, over 2. So that's 4.9 t squared plus 100t. We're going to take the derivative of that, which is now negative 9.8 t plus 100. And just like in calculus, we set that equal to 0. And I solve, and I'm going to get that t is approximately 10.2 seconds. Okay, and if you go subbing in, right, you get that h at 10.2 seconds is negative 4.9 times 10.2 squared, right? That should be squared, plus 100 times 10.2 gets me about 510.2 meters up there. So this is about 5 lengths of a football field up after 10.2 seconds. Okay, so this is how we pretty much worked things in calculus. These are actually somewhat of a more simple problem, ironically, than what we did in Algebra 2. So it's kind of like you do a more simple problem when you get to a more complex math because the math allows for it, but that math only works under certain circumstances. And we have the reality here where the function is got a real simple derivative to it, and the constraints are all just constants. So let's look at something that's slightly more complex that you might have seen in Algebra 2. So believe it or not, you actually did some multivariate work in Algebra 2. We would have said, let's minimize some function z that's equal to 5x plus 7y. See, two variables coming in. Subject to a bunch of constraints. So let's say we got 2x plus 3y is greater than or equal to 6. 3x minus y is less than or equal to 15. Negative x plus y is less than or equal to 4. 2x plus 5y is less than or equal to 27. And xy is greater than or equal to 0. Okay, so this is just a whole bunch of linear inequalities that we have to meet in order to figure out, like, where is the feasible region. If you did this in Algebra 2, you would have done this just simply by graphing. So I'm going to put up here what the graph of this would look like if I actually graphed 1, 2, 3, 4, 5, 6 constraints and what that feasible region looks like. Okay, so this is the graph that you would have seen. This is in your notes for this section. I'm not going to go and do all the graphing here. I'm assuming that you can graph linear inequalities, but here's the deal. If there's a solution to this problem, it lies in this region in the center. Now, that is that's fine. It's a matter of, okay, so like that's an infinite number of points. And you learned something in Algebra 2, and we're going to reiterate that here, that you don't actually have to test all of these points for where the optimization happens. So let's get some rules for which points do I actually have to test to figure out where that minimum might lie. Okay, so like keep in mind that we are working in a space that's a little bit more complex than just a two-dimensional reality, okay? And though the problem that we're working here only has two variables, it is possible that this could have any number of finite variables. Okay, so we're going to define things that way. We're going to define something as a convex hull. Okay, so a convex hull is going to be some region in the n-dimensional space. So we're going to let this region called omega be somewhere in an n-dimensional space. Now, if I pick 2 points in that region, we'll call one W1, we'll call the other one's W2, so that's in this region in n-dimensional space. And if I can kind of create this and I make a linear combination of W1 and W2, right, where they're the constants, and we're going to have it go between t and 1 minus t, right? So we're going to take 1 minus t and multiply that by W1 plus t times W2. This is basically creating a line segment, right, in that space. If that whole line segment is in the region omega for all t, right, on 0, 1, so the whole line segment is inside the hull, then we say that omega is a convex hull. Okay, so if that convex hull also happens to be an n-dimensional polyhedron, right, so it's like bound by taking planes that are in the n-1 dimension, right? So like we can do that, like in 3 dimensions the planes are 2-dimensional, in 4 dimensions the planes are 3-dimensional, so forth and so on. If I can do that, and then I look where the edges of these planes intersect, and then where those, so where the planes intersect give me an edge, and where the edges intersect give me what are called vertices. So if the hull is a polyhedron, then where its edges intersect, we call those vertices. And these vertices are really, 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 really important because we get this thing that we're going to call the fundamental theorem of linear programming, which says that if there is a solution to the optimization problem, then and the feasible region is a convex polyhedron, which in linear programming they will be, then that solution must be at one of the vertexes. So like we had like that 1, 2, 3, 4, 5, 6-sided, so this is like a hexagon was the feasible region that we showed earlier. So that thing's going to have 6 vertices, okay? So the answer to the optimization linear programming problem that we showed earlier is going to be at one of those 6 vertices. Now, the proof of that is beyond the scope of this course. It does make some sense geometrically if you kind of play around with it in 2 to 3 dimensions, but we're not going to go ahead and prove that here, but we're going to kind of accept that and use it to solve this problem. So if you remember in our linear programming problem from the start, we have the objective function being that we're trying to minimize z at 5x plus 7y. And if you go back and you look at the graph of the feasible region, there are 6 vertices, in fact, and those vertices are at the following values: 0, 2, 0, 4, 1, 5, 6, 3, 5, 0, and 3, 0, right? So there's 6 vertices of that feasible region. If I start plugging these in here, one of these is actually going to be the minimal value for z over that feasible region. 0, 2 lands me at 14. 0, 4 puts me at 28. 1, 5 puts me at 40. 6, 3 puts me at 51. 5, 0 puts me at 25. And 3, 0 puts me at 15. Okay, so the obvious answer here is 14 is my minimum. It occurs at 0, 2. So we've actually solved the linear programming problem using the fundamental theorem of linear programming. Now, there's a couple things that are obviously going on here. One, I could graph the feasible region because it was in 2 dimensions, and that was pretty simple. 2, there weren't that many vertices. There were only 6. Okay, but if I get into like a 13-dimensional feasible region, and the thing has like 72 vertices, this is a very impractical way. So eventually here, I'm going to want an algorithm that does some sort of hill climbing routine that moves me efficiently from one vertex to another and lets me know when I've hit the optimal point as soon as possible. And in the days to come, we're going to get that algorithm, and it's called the simplex algorithm. Okay, and we're actually going to get some code for that to make this entire problem possible and MATLABable. All right, so there you go. There's your little introduction to linear programming.